Hey guys, Chill here. Welcome back to Hardware 3D. Today we're going to be implementing a basic render queue system and rendering technique system. And this is going to be a spicy boy. Similar to the dynamic constant buffer, there's going to be lots of architectural ideas being thrown out here, but unlike the dynamic constant buffer stuff, there's not going to be a ton of metaprogramming, so it shouldn't be too hard to follow along. Now, another big difference from dynamic constant buffer is this one is not optional. It's really important that you follow the design ideas put forth here, because we're going to be expanding on this system and exploring and experimenting with it in future videos. I'm really laying the groundwork here for a lot of ideas that you see in, big engines like Unreal Engine and Frostbite Engine. So trust me, I'm going to make it worth your while to follow along with this little journey that I'm going to go on. I think we'll all learn a lot along the way. So first, a problem, and it's related to the thing that I hinted at the end of the previous Hardware 3D video. Our stenciling outline system here, it's got problems, right? And the problems, if you haven't guessed already, the problem relates basically to the interaction between the stenciling and the depth buffer. So the way we set up our stenciling, we create a stencil mask that masks out the original outline of the object. And then we draw the object, and then we draw it expanded, and the mask will give us only the outline of that object. Only if we have depth here, and these pixels aren't drawn in our normal drawing pass, the stencil mask is also not drawn for these parts here, and thus it does not mask out the object, and so we don't get a proper outline. The outline has, basically chunks bitten out of it whenever there's any kind of depth occlusion. And that's the problem here. So if we look at test cube, we can see that we have two pools of bindables here for the two different render calls that we have. We have the normal render call, draw, and then we also have here draw outline. So draw outline is going to bind the bindables from the outline effect, which is just another vector of bindables. So we got these two pools here. The first pool, it's actually doing two things at once. It's putting two operations together. The normal shading of the object, we call it the Lambertian, but it also writes the mask during this pass. So it's trying to kill two birds with one stone. But as we see here, that doesn't really work that well. So one solution would be to split it up into three. So to do that, we have to add another column here. We do it like draw mask and then draw outline. So now you have three draw calls, and we'd have three separate bindable pools. And in an app.cpp here, we'd call draw, and then we'd call draw mask in here, and then we'd call draw outline. And that would work, but I think it's not difficult to see that this is not a scalable solution. Right now we have one effect. We have the normal drawing effect, and then we have one special effect. But a real game is going to have, potentially, hundreds of effects. So now we have to add new functions and new pools of bindables for every single possible effect. That's not scalable. That's not dynamic. And right now we only really have one type of object, right? Cube, that can do effects. But in a real game, you're going to have many different types of objects. And now how do we know which object supports which effect functions? It's a hairy mess. So this is obviously not a scalable solution. Right now things are simple. We have, one render target that's bound, one depth stencil that's bound, and then we potentially have three passes: the draw, the draw mask, and then the draw outline. And there's no global changes that require different render targets to be bound or whatever. But in a real system, you're going to have many different state changes between your passes. Every pass is going to need its own special set of global things bound, and it's just going to be a nightmare to try to organize it like this. And there's another problem with this system. You notice for every pass, we have to keep same with same. So we have to call all the draws together, and then we have to call all the draw outlines and all the draw mask together. And that's fine here. Everything is nicely sorted. But in a real system, we're going to have some kind of a scene graph, like the thing we have right now, where we've got, nodes and meshes, and it's a big tree structure we call draw on the root, and that just propagates down throughout the entire tree and draws all the things that need to be drawn. But now let's say each of these meshes needs, multiple passes. It's got the normal draw pass, and then it's got the mask and the outline. So when we traverse this, we can't just, okay, draw this one, draw this one, draw this one, because that would give us a situation like this. Things are drawn in this order. But that's no good. We have to keep same with same. So what we need to do is we need to draw all the normal draws together, and then after they're done, draw all the masking draws together, and then after they're done, draw all the outlining draws together. And essentially what that means is that you're going to have to traverse over your entire scene n times, where n is the number of effect passes of all the objects in your entire scene. So if you have, let's say 200 different effects active at any given time, you're going to have to go over your entire scene graph 200 times and, traverse it once to do all the normal Lambertian draws, and then traverse it once to do all the outline masking draws, and then again and again and again. That's terrible. You don't want to do that. So what I propose that we do is that we separate the concern of traversing the scene graph from the concern of actually rendering all of the GPU commands. So these will be separated. And the way we do that is with a rendering queue, or actually multiple rendering queues. One small note before we move on, I propose that we separate the masking from the drawing, and that way when we fail the depth testing, we disable depth for when we draw the mask, and that way we don't have partially masked objects. You can actually combine these together. All we'd have to do is set the stencil op for when we fail depth testing to also write to the stencil buffer. And that would solve that problem, but it still doesn't solve the bigger problem. I mean, you can't get around the fact that you're going to need multiple passes. So even if you were to put these two together and solve this one problem with a band-aid, you still haven't solved your general problem. And furthermore, for my system, I don't want to tie this effect, this normal drawing effect, to a special effect. So while it would be a small optimization to put them in the same draw call, it wouldn't be worth it from an architectural point of view. It's better to separate them unless you're drawing a lot of outlines and you see that it's a performance bottleneck. Then you could consider that optimization of combining those, coalescing them into a single draw. But anyways, that's besides the point. So how do we separate those concerns with the render queue? Well, we add a number of render queues, basically equal to the number of passes that we require for all of our effects. So every effect will have one or more passes, and each one of those passes will have a queue. We'll call it pass. So this will be the pass for the normal Lambertian, and these two passes will be for the outlining effect. And then you simply traverse your render graph as usual. When you hit mesh nodes though, instead of immediately executing render calls on the GPU, what you're going to do is you are going to, when you call draw on a mesh, it is going to put a job into one or more queues here. So maybe this mesh is just a normal mesh, just draws itself with the normal shader. So it puts a drawing job into the pass for the normal, drawing stuff. And then as you traverse, you're going to hit another mesh. This one is drawing with an active outline effect. So it's going to put a job in the normal rendering queue, but it's also going to put a job in the masking one and the outline drawing cube. And so as you're traversing your render graph, as usual, you call draw on the meshes, but the meshes don't immediately execute drawing commands. They just submit jobs to these rendering queues. And this is beautiful, right? Because now, in the scenario that I described before, the other solution, where you're basically traversing this tree n times, one for every pass, in that situation, the traversal would have to have some way of knowing what pass it's working with. It would have to understand about passes and, techniques. With this system here, now we've completely decoupled that. The process of traversing the render graph doesn't care about what techniques there are or anything, doesn't have any idea about that. It's completely decoupled from that concept. It just traverses and calls draw on all the things. And then the things, which are the meshes, they determine, what's actually going to happen, which is going to be submitting jobs to queues. And we're free to traverse this tree in any order we want, and that doesn't affect the order of how we execute our passes. And in fact, that doesn't even affect the order of these jobs. So we submit the job to the queue in a certain order, but we could rearrange this afterwards according to some criteria. For example, with transparent drawing, you want to sort Painter's algorithm. And you could do that. You could traverse this tree in whatever order best suits the traversal, but then you would be able to sort this pass based on Z so that you get the proper Painter's algorithm back to front transparency drawing. And you could sort this pass by different criterion. For example, optimizing for state changes of shaders, or optimizing, you want big objects that are close to be drawn first so that they occlude smaller objects drawn later. That's early Z or hierarchical Z optimization. So by separating these concerns, you have a lot more freedom for, drawing things correctly in the alpha blending domain, but also for optimizing your order of draw commands. But wait, there's more. Because now that we've separated this traversal from the executing of the commands, we can start traversing this. We can start filling our render queues with jobs. And as we're traversing this on one thread, we can actually have other threads that start processing these different passes, and they can submit commands to deferred render command lists, Direct3D command lists. And this can all be happening in parallel. So you can deploy massive parallelism and concurrency with this system because everything is decoupled. And there's more, because now that we have these different passes for every render pass, these different queues or whatever you want to call them, I call them passes. They could just be dumb vectors of jobs, simple queues like that. But later on, we are going to add smart behavior to these passes so that they know what render targets they're supposed to render to, what depth stencils they're supposed to use, any kind of global shaders, whatever. That data can all be stored in these pass objects, and then the entire multi-pass rendering system can all be orchestrated, automated, and verified in a systematic way. And it's just going to make things really powerful. Like if you have a real scene where you've got maybe like 100 passes, and that's not uncommon at all in modern games. You don't want to be scripting every little detail of that manually. To be able to build machinery that can orchestrate that automatically, that can read it from some kind of separate data source, and that can verify that all the passes, they all feed into each other in the proper order, and that can optimize it on the fly. What I'm trying to say is that there's a lot of things that you could do with a system like this. But we're not going to be doing any of that crazy multi-threading stuff or any of that crazy orchestration stuff to begin with. We're going to keep it very simple to start with, and then later on, we're going to go deeper and deeper in future videos. So let's start with the fundamentals. How do the meshes know, which passes to put jobs in, and what are the jobs exactly? What information is stored in a job? These are the problems that we have to solve first. Now, in the current system, it's very simple. A drawable, and meshes are part of drawable. A drawable will have a pool of binds, and when it's time to draw the drawable, all the binds are bound, and then the draw call is called. Now, moving forward, we can't just throw all of our bindables into a single box anymore. We got to keep them sorted. We got to keep them sorted by what pass they're going to be used in. So if we have our mesh here, it's going to have multiple techniques. So one technique would, for example, be, normal shading, the Lambertian. Another technique would be the outline. And for each of these techniques, you're going to have a number of steps. So normal shading has one step. Outline has two steps, generate the mask and then draw the actual outline. And to start off with, this is how we're going to organize our meshes. They have a number of techniques, and every technique can have one or more steps. A step will then have a pool of bindables. So every step has its own pool of bindables that are, shared in the codex of bindables. So the sole step of the Lambertian technique is going to have, a shader. It's a Phong shader, basically, is what it is. But the second step of the outlining technique is going to use a solid color shader to draw the outline with a solid color. That sort of thing. So every step has its own unique set of bindables that are used to execute the step. But there's also bindables that are common to all steps. all these steps relate to the same mesh, right? So they obviously are going to use the same geometry, the same index buffer, the same vertex buffer, that sort of thing. Those are going to be common for all techniques, because if they weren't using the geometry, why is it even part of the mesh in the first place? Obviously, they're all going to use the same for those. So mesh will hold all of the common bindables, and then these steps will hold all the bindables that are particular to a step. And the final piece of the puzzle here is every step has an affinity to a pass. So this step will be submitting a job to this pass. And this step will submit a job to this pass, and this one will submit a job to this pass. Now, an interesting question is what to actually put in a job object. What sort of information do we want to store in this? And the keys to start off with here, keeping it simple. I don't want to put too much data, too much value-based data into here, because it'll make it more difficult to sort these things. You have more data to move around. So I'm just going to do pointers to start off with. But later on, when we get into performance tweaking, we'll try to see what information is better to cache in the job object and what information is better to access by reference to its original thing. But to start off with anyways, job is going to have 2 pointers. It's going to have a pointer to the step, and it's going to have a pointer to the mesh. And those 2 pointers are all that will be needed to execute a job. Because with these 2 pointers, you have access to all the bindables that are required to draw the thing. And this keeps the jobs very lightweight. It's only 2 pointers. It's very easy to push them back and to build up your render queues. All right, so to commemorate the system, I created a nice UML diagram for it right here. So let's review the entire topology of the system that we're going to create. So where to start? Well, we got drawables. That doesn't change. What does change is now drawables are guaranteed to have one of each of these things. They're guaranteed to have one index buffer, one vertex buffer, and one topology. So these aren't stored in a vector. They're stored individually, uniquely. The rest of the bindables are stored via techniques. So a drawable is also composed of one or more techniques. And a technique is composed of one or more steps. And a step is composed of one or more bindables. So step is just a pool of bindables. Technique is a list of steps. Then on the other side of the pool, you have a pass, which is our render queue. So it's just an aggregate or a container of jobs. And those jobs, they are just very simple data structures that maintain a pointer to a step and a pointer to a drawable. And when you want to execute a job, you're going to bind all the bindables for that step, and you're going to bind all these bindables for the drawable. And then you're going to, call draw primitive, draw index primitive or whatever. And then our mesh that forms the leaf of our scene graph. Mesh just inherits from drawable, and every mesh has also a matrix transformation. This is the same as we had before, right? But there you go. There's the overview of the whole thing. Put this way, I hope doesn't seem super complicated. Maybe if it does, it'll seem a little easier when you see it in actual code. I don't know. We'll see. But let's get into the actual code now. So this here is the end of the stencil buffer video. And you can see here there's a lot of commits that go into the system. But today, we're just going to look at this first commit here, because this puts down all the important stuff. All this stuff up here is just nice extras that were added on later, and that'll be the subject for the video after this video. So for this video, we're only going to look at the stuff in this one commit. There's quite a bit of it, because as you can see here, we've added, quite a few new classes to the system: technique, step, bindable, job, pass. But to start off with, we're keeping them very simple, so they should be easy to understand. Now, there's one class that I actually left out of that diagram, that's the frame commander. And the frame commander, we can see here, it is the container of all passes, and it stores basically the script of what to do for each pass. So this is what it looks like, and it is just, it's composed of one or more passes. And the way the thing works is, when you're traversing the scene graph, you pass in a reference to frame commander, and that reference is passed through the scene graph, propagates down, and when you call draw on a mesh, you pass in the frame commander reference. That gets passed through the technique to the step, and then the step will submit itself to the frame commander, which will put that job into the correct pass. And then after you're done traversing the scene graph, then you call execute or whatever on the frame commander, and the frame commander executes all the passes. So there you go. Now, the question is where to start here. And I guess we'll start with drawable. For drawable, it'll be useful to see the changes. So we'll look into here. So what we have here, we got rid of query bindable now because it doesn't have the pool of bindables. The bindable pools have been pushed down into the steps. So you don't have that. The draw command has been replaced with submit function. And like I said, it takes a reference to a frame commander. And we can see down here, now instead of having that vector of bindables, it just has bindables for index buffer, vertex buffer, and topology. And then it has a vector of techniques. And so when you call submit, it's just going to loop through all the techniques and call submit on each of those techniques and passes the technique, the frame commander, and it also passes it a pointer to the drawable, or not, a reference to the drawable. Now all the files related to this render queue system here, this pass technique system, I put them all in this filter called jobber, one for header files and one for CPP files, so easier to see them all grouped together. So drawable, submit, calls into technique. So what is a technique? Well, technique is just a container of steps. It also has a boolean to see whether the technique is active or not. So when you call submit, it's going to check to see if the technique is active, and if so, it's just going to call submit on all of the steps. Again, passing through the reference to the frame and the reference to the drawable. And then if we look at steps, we can see a step stores two things. It stores the index of the target pass. So right now we're just going to identify them by a unique index. Later on I'm going to do something better with that. But yeah, it just has the index of the pass that it's going to be submitting to. And it has the actual vector of bindables. This is the box of bindables that basically characterize this effect. And if we look at submit, which I've separated out into CPP file, it's very simple. It's just, it gets passed in a reference to the frame commander and the drawable. The frame commander has a function called accept, which accepts a job, and we just pass it a job by value. We construct that job. Jobs, they just contain a pointer to a step and a pointer to a drawable. So we construct a very simple job, we pass it in by value, and we tell the frame commander to submit this job to the pass that has this index. And then the frame commander, accept is very simple. It's just an array of passes for right now. This will be a vector later. The frame commander is going to be going away eventually. It's going to be replaced with the render graph, which is a much more advanced system. But for right now, it's just a very simple script with an array. So when it accepts a job at a pass, it just indexes into its array of passes, calls accept for the job. So what does a pass do? When a pass accepts a job, it just pushes that job back into its vector of jobs. And there you go. That's very simple. And that's the whole cycle of rendering, starting from the drawable and ending in the pass. Now, once you've submitted all the jobs, you've built up your render queues, you've got to actually execute the render queues. So that starts at the frame commander. When you call execute, it is going to draw the entire frame. So what it does is it binds any global bindables that need to be bound to the pipeline that don't change from one job to the other. So here, for the main Phong pass, we're going to be turning stenciling off, and that's not going to change for any of the jobs. So we do that here in the execute, and then we call execute on this pass. And execute just loops through all the jobs and calls execute on the job. And execute on the job, because a job contains a pointer to a drawable and a pointer to a step, it just calls bind, binds all the bindables that are associated with this drawable, binds all the bindables that are associated with the technique step, and then calls draw index. And there you have it, job submission and rendering execution. Now the third part of the equation is how do you actually build the techniques? How do you initialize them in the drawables? And to start off with, we're keeping it super simple, but there's going to be more and more advanced constructs that need to be built in the future. But for right now, all we're using is our simple test cubes. Well, let's go back to drawable. So drawable is going to have a function to add a technique, and that just pushes the technique back into the container of techniques using std move, so we can take advantage of not having to copy resources when we don't need to. This initialize parent references, we'll talk about that later. It's a little thing that we had to handle. But yeah, basically you can just, to a drawable, you can add techniques. To a technique, similarly, you can add steps. And to a step, you can add bindables. So if we look at the test cube, and we look at its constructor, we can see what's happening here. So the first thing we do is we initialize the bindables that are attached to the drawable, the common things. Vertex buffer, index buffer, topology. Then for a little organization here, I'm using scopes to organize things. I create a technique. This is a standard technique. This is our Lambertian shader. I create a step, the only step in the technique. I add the bindables required to do our, Lambertian Phong shading. And when we're all done that, we add this step to the standard technique, and then we add that technique to the current drawable. And then the second technique here is the outline. It has two steps. So we create the masking step, we add that, and then we create the outline drawing step. We add that step to the technique, and then we add that technique to our drawable. There you go. And for these techniques, it's very simple. Like I said, the masking step, we're not drawing to the render target. So what we actually do is we bind a null pixel shader, and that will stop the engine. We bind a null pixel shader, and that will stop the pipeline from trying to draw to the render target. So it'll only draw to the depth stencil in that case. And then for the actual outline drawing, you can see here that we add the pixel shader, the solid one, solid vertex shader. Here, instead of the normal transform cbuff that we normally use to get the, basically to link the transform matrix into our vertex shader, we need one that also scales the object up by a little bit. So what I did was I just created this inline class here, inherits from transform cbuff. It overloads or overrides its bind function to add some scaling in there. But yeah, that's basically it. You might be wondering, well, Chili, where I don't see any stencil being bound here, and I don't see where you bind the null pixel shader in here. Where is that being done? And well, because those states don't change over this entire pass, what we can do is in the frame commander, we bind that globally before we execute the pass. So here we bind the stencil off, here we bind the right, here we bind the mask, and for the outline masking pass, we can just bind a null pixel shader here. In fact, I mean, we could have probably just bound the solid pixel shader here for this pass, because that's also doesn't change from object to object, but you get the idea here. So we can factor out common bindables, put them in this script here, and that makes the work that we have to do during our jobs a little bit lighter. If you're interested, here's the null pixel shader. It's very simple. All it does, it doesn't have to create anything because it doesn't bind anything. It's just when you call bind with the null pixel shader, it just uses a null pointer with PS set shader. So another nice little showcase of how our bindable system works very nice and dynamically. Now there's one last thing we have to talk about regarding the initialization of our techniques. And that's this thing here, initialize parent references. You see it in technique, you see it in step, you also see it in bindable. And this is a little tricky to explain because this is actually some planning for the future. So we haven't encountered the problem that requires this yet, but we will encounter it in the future. So let me just quickly lay out the problem. So with our current little test here, our test cubes, let's call it test cube, has a CTOR constructor, and in that constructor, it is defining all of the techniques. And that's fine for our little test. But in the future, what we're going to have is we're going to have a bunch of meshes, and we're going to have some technique templates, and we're going to want to add techniques to meshes from this template. We don't want every mesh to have to describe in its constructor how to create this technique. We don't want to duplicate that between different meshes. What we want is we want to have these techniques loaded into memory, and then we can just add them to whatever mesh we want. And we can remove techniques from meshes dynamically at runtime. The problem with this is that some techniques, well, pretty much all techniques, are going to have bindables like transform cbuff, right? And transform cbuff requires a reference back to the drawable, because it needs to get at the transform matrix that bindable holds, not the bindable, that the drawable holds. So that's a problem, right? Because if we're templating this technique, we're copying it. If this transform cbuff has a pointer to a specific transform, if we copy it here, when we draw this mesh, it's going to get this transform. It's going to be drawn in the wrong position. So what initialize parent references does is when you add a technique to a drawable, it basically goes through that technique, it goes through all the steps, and if there are any bindables that need a reference back to the parent drawable, it will initialize that reference. Allow me to demonstrate with a concrete example here. So we got test cube. We are constructing these techniques. And you'll notice when we create the transform cbuff, it doesn't get a reference to the drawable, the test cube. So what happens? Well, you add this bindable to the step, then you add this step to the technique, and then you're going to add this technique to the drawable. And when you call add technique on a drawable boy, what it's going to do is first it is going to initialize parent references, call that on the technique, and pass in a reference to itself. So if we go to technique, initialize parent references, what this is going to do is this is going to loop through all the steps and call initialize parent references. It's going to pass that parent reference down the line. So when step gets its parent reference, it is going to pass that down the line to all of its bindables. Now bindable, we've added this virtual function, initialize parent references. By default, it does nothing. Most bindables don't care about having a reference to the parent. So for most bindables, this isn't going to do anything, except for some special ones that want to track a reference to their parent, like, for example, transform cbuff. So transform cbuff overrides initialize parent references, and what it does, it just sets pointer to the parent. So I've changed the parent reference to actually a const pointer, but it's the same idea, right? And there you have it. I believe that is basically all of the important changes. Then in app.h, we add the frame commander. And in app.cpp, what do? Cubes, set the positions of the cubes. That's fine. So we submit our drawables to the frame commander. And then we call frame commander execute. And it executes the drawing. So that's very simple at this level. You've seen the changes, the bindable here, drawable, frame commander, job. What about input layout? We added a function to get that layout. All right, not a big deal. No pixel shader, mesh. Mesh obviously now requires submit. So we change from draw to submit. But it's all basically the same stuff. Well, actually, there's a lot of changes in here. A lot of things basically just commented out. I basically just commented out most of this stuff just to get the simple system working, because we haven't actually converted over our meshes to use the new render queue system. So this was just commenting things out to get the damn thing to compile so I could do my test. But yeah, that's it. So let's run it. All right, and here we are. We're back in the void with our two cubes. But now if you see, if I make it so that the light occludes, now we don't get that weird artifact. What we do get is the outline still shines through there, which is what you want. You want that outline to be visible no matter what's occluding the actual object itself. But we don't get it where the entire light indicator turns red, which is good. So this is the system working, but now we really have our work ahead of us, because we have to now port this system over to our mesh node hierarchy scene graph thing. And that's what these commits up here are all about. Well, they do a lot of things, but that's one of the main ones that is being done. And in doing so, we're going to fulfill some promises that we made earlier. Remember when we implemented the dynamic vertex and the dynamic constant buffer stuff, that was so that we could create a dynamically composable mesh loading system. And we're going to implement that as we implement the techniques into the meshes. It's all going to come together. We're also going to take advantage of the new dynamic reflection that we have with the dynamic constant buffer. And we're going to create something called a technique probe that can probe into the node tree and allow us to dynamically manipulate the constant buffers. So stay tuned for the next video. It's going to be a big ass crazy balls upgrade to our node mesh hierarchy, and it's going to be pretty sweet. Until then, thanks for watching. Hope you enjoyed this video. If you did, please click the like button, helps a lot. And I'll see you soon with some more Hardware 3D.